Welcome to the last class. You are almost done. Um, Hopefully this wasn't too painful an experience as we all try to figure out this online thing together. Um, but yeah, I'm ready for this to be done too. Summer classes are an intense bunch of weeks that I'm ready to start doing something else. Um, Couple of so today. Whoa, that's exciting. Where are you? What is going on with this? Today, the end. Um, so we're gonna do the last of everything today. I was gonna do a bunch of cool AI stuff and talk about like what kinds of things you can and can't write algorithms for. I might still do that, but I figured you'd get more out of me spending time going over at least part of the lab to see how to do that kind of stuff so you're ready for the homework. So we'll see what happens there. Remember, well, that's what's happening. All right. I think after doing this 10 times, I'd be better at it. Homework 5 and final are due Monday, not Tuesday. Um, my grades are due Tuesday. Um, Kinda. Often I will curve it. I might curve it more, or I mean, so usually I curve things by grading nicely in the sense that I could take off more points on the homeworks and I don't, and I give you higher grades than I might otherwise do. If I still need to curve things after that to make it come out right, I will. So I guess the answer is certainly 90 is an A. It's quite possible that something below 90 would also be an A, depending on how the curve comes out and how you guys do in the final and blah, blah, blah. So I don't have an explicit preset curve. I curve based on how things look after all is said and done. But if you're doing math and think that you have, no chance of getting higher than an 88 or something like that, an 88 might still be an A. Who knows? Haven't graded the fourth homework because not everybody's handed it in yet. You know who you are. I will grade that as soon as I get all of the homeworks. I will grade homework 5 as soon as I get it on Monday or Tuesday. I'm planning on spending all day Tuesday grading. If you know you're going to have it done and want to hand it in sooner, you will make my life easier so I can start grading things earlier. Trying to grade 8 people's final homeworks plus final exams in one day, it has to be handed by 4:30 on Tuesday, is going to suck. So making my life easier would be nice, but I want to give you as long as possible to do the homeworks if you need it. So that's the plan. All right, so yeah, it's really due Monday, and it's not my deadline; it's the registrar's. So you can't really extend it past Monday. So having said that, what we're doing now is designing and analyzing algorithms and stuff using the Big O notation. I want to do a couple more examples of that today, but if you have any questions about what we've been doing or questions about the homework, now is the time to ask them. So um, I'll answer any specific questions you have about stuff we're doing or any general questions about things you don't understand. Otherwise, I'll start wandering through the lab a little bit and see if I can find some examples of things to do and walk you through walk you through how I want you to do that and get the big O and stuff like that. So let me know. So any questions on what's going on so far? Going once. Going twice. Okay. So let's see. I'm looking at the lab now. The first thing in the lab was design an algorithm that takes a list of numbers and finds the smallest thing in it. We did that last week. We said basically we have to look at every number and remember the smallest thing we had Tuesday, not last week. It'll look at every number in the list and remember the smallest thing we ever saw. So it was. So why does that keep happening? I don't think this happened last time. I wonder if there's a. What's happening is when I put my hand on the screen, it's marking it. And I don't think that used to happen. I think I used to be able to leave my hand on the screen and only register my pen. So, yeah. So lab. Number 1, we did on Tuesday. Looking at all n items once was order n steps. Number 2 says using that algorithm we can sort, and I think I did this on Tuesday as well, by finding the smallest thing, taking it out, finding the next smallest thing, taking it out, and repeating that process over and over and over again. Also Tuesday. And so show how this algorithm works on the list 3, 1, 4, 6, 2. So here's my list. Find the smallest. So what I do is I walk through the whole list and remember the smallest thing I've ever seen. So right now 3 is the smallest, and then I go down to the 1 and I say, nope, you're the smallest. But then I still have to check everybody else. And the 4 is not smaller than the 1, and the 6 is not smaller than the 1, and the 2 is not smaller than the 1. So the 1 is the smallest. Remember this? And the 1 is the smallest, and I pull out the 1. And what's left is the 3, 4, the 6, and the 2. And then I find the smallest in there. I start by looking at you, and I see if anybody else is smaller. Eventually, the 2 is the smaller, and I get the 2. And then remaining is 3, 4, 6. And so on and so on and so on and so on. Okay, and so next I find the smallest. And I look at everything in the list. The smallest thing now is 3. Remaining is 4 and 6. And then I find the smallest. I look at both items. Pull out the 4. Remaining is 6. And then find the smallest thing in a list of just 6 is 6. What's left is nothing. And so if you go back and look at all of the stuff I pulled out, you'll see this list going all the way down has all of the numbers in numerical order, right? So, and then it says, what's the big O of this? And so what I'm saying, so it turns out, find the smallest is order n. Do it n times. N is always the number of things in the list. Okay. N times order N. Whoops. Equals order N squared. So I got an order N squared thing by, whoa, that was ugly there. I got an order N squared thing by doing an order N thing N times, because N times N is N squared. Okay. So that's number 2 in the lab, which showed how you can use an algorithm like the one from question 1 as a step in a more complicated algorithm as time goes on. All right. So so far so good. This is all stuff we did on Tuesday, I think. So question 3 is the first time that's different. Okay. Question 3 says design an algorithm. Yeah. 3. Find all numbers that divide evenly into a given n. So in this case, I don't have a list I'm handing you. I'm actually building a list of all of the numbers that go into n. Okay, so if n is 15, 1. 15 divided by 1 is 15 with no remainder. 15 divided by 3 is 5 with no remainder. 15 divided by 5 is 3 with no remainder. 15 divided by 15 is 1 with no remainder. So I would list out 1, 3, 5, and 15 as all of the numbers that go into 15 evenly. 12 does not divide into 15 evenly. It has a remainder. So basically the algorithm and I think of this in terms of variables, like we had variables in the Scratch program for position and speed and stuff like that. But so my current divisor is 1, and then see if n over current divisor has no remainder. So try it. So basically what I'm going to do is start at 1, try dividing n by 1. That's certainly going to have no remainder. 2a, if no remainder, output current divisor. So if it goes into it with no remainder, then hooray, output the current divisor. All right. Then add 1 to the current divisor, moving it on to the next thing. So now it will be 2. And then if current divisor is less than or equal to n, go back to step 2. So this is a more formal listed out the steps way of doing it, where I list out a variable and I increment it and stuff like that. And what I'm doing is I'm trying every possible number. If you said something like this, try dividing all numbers from 1 to n in order. Any that divide easily gets output. I'd be okay with that too, okay? Because I know how to do that, all right? I know how to divide, I know how to go in order from 1 to n. My algorithm up top just gave that thing I was dividing an explicit name. I think that makes it easier to understand and see what's going on. If you say something along these lines, then I will understand what you're saying. The point is, though, you need to give me an order, and you need to tell me what the range of numbers you're dividing is, so I know where you start and I know where you stop. Okay, because um, I, I I have to have a process to do this, right? With 15, maybe you can do it in your head. With 15 million, finding all the numbers that divide into 15 million, you need some kind of process that makes sure you don't skip over anything accidentally. And so this gives me a process that I would not skip over things accidentally. Okay. Either way, what you're going to get at is I'm doing n divisions, so this algorithm is order, and it's about n steps. I do about n things, right? Because I do about n trying to divide and spitting stuff out. And the reason we're using big O instead of actually counting the number of steps is I don't want to get bogged down into counting the exact number of things I do. I don't want to get bogged down in counting how many of these, why is this so slow? How many of these step 2A's there are. And so I don't know exactly how many, come back. And so I don't know exactly how many steps I'm going to do. It depends on the number. But I know I'm going to go through this sequence of operations, this loop, if you want to think of it in Scratch terms, n times. And that's all I care about. That means I'm going to do about n steps. And that's where the big O idea comes from. Does that make sense? Hopefully your silence means you're understanding and not that you're so lost that you're not saying anything. All right. Moving on. Let's see what the next one is. Number 4 says, see if a number is odd or even. And so you guys, I don't know if you guys, oftentimes in school you learn a trick where you can look at a number and instantly see if it's odd or even. Do you guys know what that trick is? Even if the number had 8,000 digits in it? You can divide by 2. Certainly if you divide by 2 and have no remainder, it's even. But yeah, well, that's it. Look at the last digit. So if I give you this number, 29,475,312, even or odd? Even. Instantly, right? And it's instantly even because the last digit's 2, and that's all you need to know, right? I don't need to divide. I don't need to do a whole bunch of steps or anything like that. I don't even know how I would divide this number. It would just take me forever. So step 1. So this is an easy algorithm. Is the last digit 0, 2, 4, 6, or 8? 1A, if yes, it's even. 1B, if no, it's odd. And that's it. That's my entire algorithm. Okay? And so this, I would say, is one step, order 1. About 1 step. Okay? I don't do more work based on whether the number is bigger or smaller or not. Doing the find all factors one, if I took my number from 15 and made it 15,000, I'm doing a lot more work because I'm doing a lot more divisions. Here, if I take my number from 15 to 15,000, all I'm doing is looking at the last digit anyway, right? So no matter how big the number is, I only do one thing, and that one thing is look at the last digit. Okay, so order n means you're doing something over and over and over again until you hit the end of all n things, whether n things is the number of items in the list, or n things is all of the n numbers less than or equal to the number I handed you. Order 1 means no matter how big the number is, I only ever do one small thing and then I'm done. Okay? So that's I wanted to show you these to show you the difference of n and order n and order 1. Does that make sense? So one step versus one step per item or per thing. Okay. All right. Here's the next one. Number 5. So hopefully you guys at least looked at some of these. I don't know how many I'm going to be able to get through, but and what I'm saying here is confirming the stuff you did. Number 5. An algorithm to see if two people in a class, or really any group, have the same birthday. So the idea is you show up in a room full of people and you want to know whether two people or more in that room have the same birthday. Okay? And the only thing, and so what one step is here is seeing if two people have the same birthday. Okay? So, and keep in mind that that one person is doing this. So if I make all of you guys yell out your birthdays, what's going to happen is everybody's going to kind of in parallel at the same time look up their birthdays and see if it matches. What has to happen is one person, or if you rather, one computer has to kind of take all the birthdays in and compare all of them against each other to see if two people have the same birthday. So my algorithm for this is write down the first person's birthday. Step 2. Write down the next person's birthday. Okay. So now at the moment, I have two people's birthdays on the board. Okay. But I'm going to do this by, here's the picture I want you to think of. This is my birthday. October 25th. Then a second person shows up and they write down their birthday. And what we're going to do is we're going to see if it matches anybody who's already on the board. Okay? And then the third person shows up and we're going to check them against everybody who's already on the board. Okay? And then the fourth person shows up and we're going to check them against everybody who's already on the board. Okay? So every new person that we get has to compare their birthday versus everybody else's birthday that's already happened. Okay? So going back to the algorithm, what I'm going to do is I'm going to say check this new birthday versus all previously written ones. 3A, if any match, you found a match. So we're going to come back to this step in a minute, but the thing I want you to notice now is that This step involves a lot of checks, potentially, right? If I've got 10 people already on the board and I add an 11th, this 11th birthday needs to check against all 10 people already on the board. So this one step I wrote down is really lots of checks. Okay? And we're going to have to count how many in the end when we start figuring out the big O. But just so you know, one step I write down could hide lots of different stuff. Okay? And then step 4 says if people exist who have not been processed, go to step 2. So step 4 says, after I've checked this one person against all the birthdays on the board, see if there's anybody else who has not been written on the board yet. And if they haven't been written on the board, go back to step 2, which was the write their name on the board, then go to step 3 and check them against everybody else, and so on and so on and so on. Step 5 says when all people have been processed, you know all birthday pairings. And so you know if anybody has matched, and if nobody has matched, then you know there is no possible matches. Okay? Now, figuring out the big O of this, involves us thinking about all of the hidden work that happened in step 3. The hidden work in step 3 was the work of looking at everybody else in the that was already been written on the board and seeing if there was a birthday in there. So step 3, I have to look at all other dates on the board. In the worst case, and we talk about the worst case, how bad could it possibly be? That's order n checks, right? N because it's n people in the room. Maybe it's order n minus 1, but n minus 1 is about n. Since I do step 3 for all n people, that's order n squared steps total. So this is another example of an order n squared thing with kind of a hidden step, because the rule is checking a pair of birthdays is one step, and so I have to kind of check all pairs of stuff. Another way of thinking about it this may be a little mathier. I have n people, each can pair with n minus 1 other people. So that is about n times n minus 1 equals order n squared pairs to check. And so that would be another algorithm if you want to say, take all pairs of people and check their birthday. That's n squared pairs. I like my step-by-step algorithm better, but if you don't want to think that way, if you kind of have a general feeling for how this works and you want to go by that, that's fine. Either way, though, you have to say, I have to check all combinations of people, and that'll get you to n squared. Okay, so when you do this on the homework on the test, I want to see both the algorithm and the big O you get out of it explaining how fast it is. One of the cool things that I can do with this in a class of 20 or 30 people is it turns out that in a group of, I think it's 30 people, there's a 50% chance of having a match. Which seems super, super high, right? That it's 50-50, that two people have a match, that two people have the same birthday in just a group of 30, because there's 355 possible birthdays, and pulling just 30 people seems like you'd have like a, I don't know, 30 in 365 chance of them all matching. But the reason is because of all of the n squared combinations of stuff. There's lots and lots of different possible pairings out there, and so the number goes pretty high. In a group of 40, I think it's 40. The chance. Whoa! I'm on a whole different page now. Goes up to 90%. So it doesn't take. This is a fun party game if you want to impress your friends or something like that in the frat house. Get a group of 30 or 40 people together, make them all write down their birthdays, and you will almost definitely have two people with the same birthday. And it seems like 40 is not enough to make that happen because there's only 40 with all the different days. But because of all of the different combinations of pairs there are, it gets pretty likely pretty fast. So, hooray. Let's see. What's next? The bank balance one is just like the bank balance. This one says, given a list of people and their bank balances, find all people with negative balances. This is a lot like the find all divisors problem. The find all divisors problem said walk through all of the possible candidate numbers and spit out the ones that matched. This, what we're going to do is look at all the accounts. If the account I'm looking at is below $0, output it. Order it. So I look at everything in the list once. As I look at it, I see whether it's something I need to output, and in this case, the is it a thing I need to output question is are you negative. In the divides evenly question, the are you a thing I need to output question was do you divide evenly into n. Either way, if it matches your criteria, spit it out. Looking at everything once is order n. Let me Is this helpful to you guys? Are you following along? Are you doing the lab? Okay. Is there a thing in the lab that you got stuck on that you want me to do, or do you want me to just find one that I think you might get stuck on later? Or the homework, actually, if you look at the homework. Because otherwise, I am going to try to probably jump ahead to number 10 because it's different. All right. Number 10 says, here's a problem that's slow. Order 2 to the end, towers of Hanoi kind of slowness. Here's a shortcut. That's faster. And then how fast is the shortcut? Show where it's wrong. So the idea is I hand you a problem that has, that I'll just tell you has worse. If I'm going to run it and find an exact answer, I got to do something as slow as Towers of Hanoi, which was doubling the amount of work by adding one thing to the size. Remember that with the disks? And then here's a shortcut that's faster than that. How fast is the shortcut? And then show why it's a shortcut and why it doesn't solve, given a situation where it won't solve the problem exactly. All right. So the first one, Indiana Jones. So the idea of the Indiana Jones problem, okay, is you're Indiana Jones. Maybe I'm dating myself, but I like drawing Indiana Jones because he has a hat and he has a whip. And Indiana Jones is in the temple of whatever, and he sees a bunch of treasures. And I'm not going to be able to draw treasure. These are all like monkey idols or whatever. Fork. Whatever they are. Okay? Every treasure has a profit and a weight. The profit is, these are just numbers. The profit is how much it's worth. The weight is obviously how hard to carry. Okay? So you're Indiana Jones, you show up, you see these treasures, they have a profit, each treasure has their own profit and their own weight. You can only carry, in the homework I say K pounds, where K is predefined. So you can't carry everything. You can only carry some amount of weight of stuff. And so the question is, what do you take to maximize profit and not exceed your carrying capacity? Okay, so how do I make as much money as I can while not going over my weight allowance? Okay, so I don't know if you have the lab open or not, but I give you a table, and as an example, item profit weight. Item 1 makes me $3, weighs 2 pounds. Item 2 gets me $4 and weighs 4 pounds. Item 3 makes $5 and weighs 1 pound. Item 4 gets me $6 and weighs 3 pounds. Item 5 gets me $7 and weighs 6 pounds. Okay? And K equals 6, which means I can carry 6 pounds. Okay? So in this example, some things I could do, I could take just item 5, and that'd be my whole 6 pounds right there, and I make $7. I could take item 2 for 4 pounds, and item leaves me 2 pounds left, so I can take item 1. Between those two, they get me 6 pounds, and I make $7 as well. The shortcut algorithm says sort by profit per pound. So figure out what everything's worth in terms of dollars per pound you're taking, and take things in decreasing profit per pound. So what the shortcut algorithm wants me to do is make a third, make a third row. I'm going to erase this k equals 6 to make room for my row. And I'm going to write k equals 6 down here. Okay, so $3 for 2 pounds is $1.50 per pound. $4 and 4 pounds is $1 per pound. $5 and 1 pound is $5 per pound. $6 and 3 pounds is $2 per pound. See how I'm getting this? And $7 and 6 pounds is 1 and it's like 16, whatever 1/6 is, dollars per pound. Okay. So what that means is what I'm supposed to do is take U first, and now I've used 1 of my 6 pounds, and then I'm supposed to take U second, and that's to use 2 of my pounds, 3 of my pounds, 1 plus 2. I'm supposed to, I can't add. I'm supposed to take U second, because $2 per pound is better than $1.50 per pound, and that's used 4 of my 6 pounds of allowance, and then the next highest price per pound is U, and now I've used all 6, and that makes me $14, which is way more than the 7s I was showing you before. Okay, so in this specific situation, the shortcut algorithm works. Okay, so the first question is, what's the big O of this? And what we saw from before is that sorting something took about n squared steps, at least the way we know how to sort it. Okay, we could use that selection thing we did in question 2, where we select the smallest out and keep pulling it instead. And then this is about n more steps to look at all of the items one at a time and see if I could take it. Okay, so remember, big O drops lower terms, so that whole thing adds up to about n squared steps. Big O is all about dropping lower terms and dropping constants and things like that. So now the second question is, find an example where this fails. So what we got to do now is we got to find a situation where this shortcut is wrong, where following the shortcut makes us less money than not following the shortcut does. And so this is actually pretty hard to come up with on your own. The way to think about it is probably a case where the shortcut leaves empty carrying space. So imagine, for example, a situation like this. And this is a very super easy situation, okay? I can make $5 taking 5 pounds of stuff, or I can make $4 taking 3 pounds of stuff, and my capacity is 5. Okay? I'm going to, again, not stupidly overwrite the third column I was going to make. The ratio here is $1 per pound, right? The ratio here is 1 1/3 dollars a pound. So the shortcut makes $4 because it told me to take the thing with the best ratio. And then I have 1 pound of empty space in my backpack that I can't, actually 2 pounds of empty space in my backpack I can't do anything with. But I can make $5 taking item 1. All right? So this is what I mean by show a situation where the shortcut fails. Okay? The shortcut, if I follow the algorithm, I got to follow the algorithm even when it's wrong. And so here's a situation where the shortcut algorithm is wrong, and I should have not listened to it and done something else instead. Okay, so this is why this turns out to be an example of a problem where the only way we know how to do this and be sure we're exact no matter what the situation is to basically try all combinations of taking and not taking stuff in my backpack and seeing which one's the best. And it turns out there's 2 to the n of those subsets. It's the power set if you've done that in math and things like that. But the point is, any shortcut you come up with for this problem, I can come up with a situation where your shortcut's wrong. Where if you follow that shortcut, I can give you a situation where your shortcut will give a smaller profit than what the right profit would have been. Okay, so question 10 is asking you that one. Let me see what else I'm doing here for question 10. I think I give you a second one. Yeah. I give you 4 of these, so let me do one more to show you how this works, and that'll probably be enough time for today. So problem 2 is called the Halloween candy problem. Halloween candy problem says, it's Halloween, and you're all about finding the houses that give the good candy. If you're anything like I was when I was a kid, there's certain houses in your neighborhood that gave out the good candy, and certain houses in your neighborhood that gave out Tootsie Rolls and toothbrushes and crap like that. We want the good candy. So suppose you've marked out, because you're a computer science person and you want to think about algorithms, a bunch of different houses, and these are the 4 houses that have good candy. This is your house. Okay, and this is how long it takes you to walk from one house to another. Maybe you're cutting between yards. Maybe one of these roads has a dog on it. There's not necessarily any relationship between physical distance and time here, because of the way roads work, and maybe you're cutting through a backyard or something like that. I need to visit all houses exactly once and return to the start. in the shortest time. And my Halloween candy example is kind of silly and fun and stuff like that, but this is a real problem that real businesses have to follow, right? If I want to send a one of my salesmen around on, you can think of these as cities, and the distances being airline costs, and I want to send you on a tour to visit a whole bunch of cities that you want to sell stuff to and then get back to home. How do I do that, minimizing my cost and minimizing my time? So there's lots of real world applications of this problem if we could get it to work fast. Okay. What the shortcut is, find the shortest connection from where you are to what's next. And take it. If it's a tie, take whichever one you want. Okay. So up here, what I would do with my shortcut is I'd start at A, and I have color. I'm going to draw this in a color. Look at me. I'm going to start at A. Ooh, it's red. And go to B, because that cost me 1. I'm going to start at B, look around at all of the other places I can go, and go to C. When I'm at C, the cheapest place I can go to is D. And when I'm at D, the cheapest place I can go to is back to A. And that gets me all around the entire circle for a total cost of 5, right? So that's the shortcut algorithm. And 5 should not be the fastest thing you can do in that situation, okay? So first question is, what's the big O? At each city, I need to check costs to n other cities. So that's order n. So figuring out what the cheapest way out involves checking every single possible direction. So there's n possible directions. And I visit n cities. So I'm doing an order n thing. Order n times is order n squared. Okay. So this one's n squared because I have to check all of my neighbor cities from where I'm standing. That's n checks. And then I have to do that check of all my neighbor cities from every single city I visit, and that makes it n squared. Whoa. Where does it fail? If you were paying attention, remember, I'm only allowed to visit everybody once, okay? Exactly once. So if you go back up to here, and you remember that I have to visit everything exactly once, and you walk through the path I took, okay? I went from A to B. I'm going to draw this in blue now. I'm excited about my colors. I went from A to B. I went from B to C. I went from C to D. Now, if I'm sitting at D, okay, I'm not allowed to go back to B. I'm not allowed to go back to C. I have to go back to A, which means I'm taking this edge no matter what. It's the only edge I could possibly take. Okay, so this road is the only road I can possibly take. Okay, so no matter what that road costs, I'm paying it. Okay, and if this road instead of 2 cost 200 million, I still have to take it because the algorithm told me to start at A and then find the smallest way out of A, which was going to B, and then find the smallest way going out of B, which is going to C, and then find the smallest way going out of C, which is going to D, and then find the smallest way going out of D to home, which was the only choice I had, was to go home along A. Okay, so the problem that so this shortcut runs into a problem because at the end you only have one choice to take to get back from the last house back to your house, and if that last road is super slow, oh well, you're stuck. Okay, so hopefully this has gotten you thinking about algorithms. Hopefully this is making your life easier on the homework and on the final. Thinking about algorithms is the kind of thing that sometimes you need to kind of have running in the back of your head and try a couple of ideas before it works. So do give yourself time to do that. As always, if you have any questions about the homework or even the final and want to ask me about them, please do ask me about them, and please also ask me about them early enough so that you give yourself enough time to have my answer and be able to do something with my answer. All right? Any other questions on this stuff? Going once. Going twice. Well, all right then. Thanks for putting up with this semester. I think you guys all have come through our technological challenges well, and this is a new experience for all of us, and I think we've done pretty well. I think this was pretty successful. I guess you guys can decide for yourselves. Do let me know what you think about this class and what you think can be done better if you want. I think they're going to do a survey at the end, but I'm not sure how that's going to work. So if you have any opinions on the onlineness of the class or how it's organized, and how it can be better for next time, I'd love to hear it. Other than that, I will see you guys. Well, I was going to say I'll see you guys next week, but I won't. So good luck, and maybe I'll see you around next semester. Pop by and say hi so I can see your faces. Other than that, good luck and everything, and I will see you around eventually. Bye, everybody. End the recording.